we introduce zero-error tracking for autonomous vehicles through Epsilon-Trajectory generation. We present a nonlinear control method that guarantees asymptotic convergence for vehicles with first-order non-holonomic constraints. We do this by controlling a point in front of the vehicle and tracking a new reference trajectory generated for that point. To start, imagine you have a two-dimensional vehicle such as the kinematic bicycle model, boat, some aircraft, or the unicycle model. They cannot move orthogonal to their direction of motion. Vehicles of this type are not completely controllable. So our paper extends a novel method of controlling a point in front of the vehicle, referred to as an epsilon point. Because this point does not share the same motion limitations as the model, it can move freely about. By doing this, you remove the non-holonomic constraint while still keeping a time-dependent controller and guaranteeing convergence of the point. Unfortunately, by the same token, when you control a point epsilon in front of your vehicle, you will always have a steady-state error between your reference point and the desired trajectory, which brings us to our major contributions. To begin, we will explain epsilon tracking and discuss how it can be extended to other models, such as the bicycle model. Following this, we propose generating a new trajectory intended for the point in front of the vehicle, that when tracked using epsilon tracking causes convergence. Next, we prove asymptotic convergence using a change of variables and a Lyapunov candidate function. And finally, we explore trends of our simulation results and offer a brief analysis. Now to epsilon tracking. I'm going to give a high-level overview of what epsilon tracking is and explain basic concepts of controlling a point in front of a vehicle using the original system inputs. Suppose you want to control a vehicle with the unicycle model dynamics and acceleration inputs. However, this system is not completely controllable, so let's turn our attention to a point in front of the vehicle, a point that is a distance epsilon away. We define the point as q epsilon. It can be described as the x and y reference location plus a distance epsilon in the direction of heading. Now, for a moment, assume that we can control the inputs to the point q epsilon directly with double integrator dynamics, and let the control matrix be u epsilon. The reason we use q double dot as the input is because we want to match the inputs of the point to the vehicle inputs, because that's ultimately how we'll control the point. Now, let's introduce the state P to formulate a very straightforward system, which turns out to be completely controllable. So to connect the idea, if we can find a way to describe the inputs to the point in front of our vehicle, q epsilon, in terms of the inputs to our actual vehicle, we are not limited by our first-order non-holonomic constraint. It is as if our vehicle is now completely controllable. But a more exciting part is that this approach holds for other models too. In our paper, we show how to use a similar algebraic substitution with the bicycle model. Shown below are its dynamic equations. Note that it has an additional non-holonomic constraint on the front tire, which produces a limitation that it can't turn 90 degrees. As such, when solving the algebraic mapping between q epsilon and the vehicle inputs, you see the limitation appear on steering input, where forward velocity cannot approach zero. Despite this, the same control law developed for the leading point can be used on other models. But now to address the fundamental problem of epsilon tracking. We still have the steady-state error between the epsilon point and our reference trajectory. Well, why don't we just let epsilon go to zero? Make it negligible. Though theoretically possible, in practice, the matrix R inverse scales the input to the epsilon point, and as epsilon approaches zero, the commanded input is multiplied by infinity in the presence of error. What's more, when you have sensor noise, a small epsilon accentuates this problem, which is why we propose a method that achieves zero-error tracking by using epsilon trajectories, meaning we create a new trajectory intended for epsilon tracking that eliminates the steady-state error, regardless of the length of epsilon. You can see what I mean in the figure on the right. The green line is the reference trajectory, and the orange line always leads the green by 5 meters. It's the epsilon trajectory. Notice that these two trajectories have a different position, curvature, and even heading. Their only similarity is that they maintain a distance of 5 meters. Because of that, if we match our epsilon point accordingly, we will always lag the orange line by 5 meters. The result? We end up tracking the green line. Watch this animation to see what I mean. The blue car is our system, and we want to converge to the green dot by tracking the orange. We control the blue X to the orange epsilon trajectory, and we make it. Okay, let's watch that one more time. As we drive to the orange dot, we converge to the green, our original reference trajectory. Now, I will give you an overview of how the orange epsilon trajectory is created. Consider the original green reference trajectory. We want to create a new trajectory that leads this one by the same distance as our controller. First, we calculate what the vehicle state would be at every point on our reference trajectory. This is possible because our system is differentially flat and we have a sufficiently smooth path. We can do this with nothing more than the reference trajectory position and its three derivatives. As seen below, we can calculate heading, velocities, and the system inputs at every state. With the vehicle states in hand, we can then calculate q epsilon for the reference trajectory. That's the green X in front of the calculated vehicle. Then, using the dynamics of q epsilon, we can calculate the states of the epsilon trajectory, and we have successfully built a new trajectory for our controller, seen in orange. This is a key idea. We are using the same linearization technique on the reference trajectory from earlier to create this new trajectory for our controller. Now, as our vehicle in blue tracks the orange epsilon trajectory with a steady state error of 5 meters, we start tracking the reference. In this figure, you now see two vehicles. The blue is our actual system and the green is what our system would look like if we were tracking the reference trajectory perfectly. It intuitively makes sense that when two vehicles are constantly driving towards the same point, they will eventually come together. Which brings us to our proof. A helpful way to consider how the vehicle converges to the desired trajectory is to only consider what happens after the two epsilon points near each other. That's because we prove in our paper that the epsilon point converges with a reference trajectory at an exponential rate, or as shown in figure A, you can see the leading point of the blue vehicle begin to converge with the leading point of the green vehicle. So, as both epsilon points near each other on the epsilon trajectory right here, we can think about the problem in a different way to analyze how the two vehicles settle onto each other. Instead of considering two vehicles driving towards the same point, figure B shows that it can be viewed as a single vehicle pulling two trailers that are attached at the same point with the same length hitch. This is significant because the dynamics of a vehicle pulling a trailer are straightforward, and the stability of our system can be defined by the trailer heading error, one variable. As long as the heading of both trailers converge, we know both systems have converged. We later propose a Lyapunov candidate function that guarantees zero error tracking. This creates the foundation for our simulation results and conclusions, so feel free to look it over. I will now briefly outline some of our tests and their related trends. In our paper, we also perform Monte Carlo simulations with varying sensor noise on different trajectories, with different models, and with isolated initial errors. But for this presentation, I will explore a single case without noise that highlights the effects of increasing epsilon. Consider the tracking simulation with initial heading error of -2 pi thirds. This example highlights how epsilon affects convergence. Starting out with an epsilon value of 0.5 meters, the vehicle turns and quickly converges to the reference trajectory. Now, if we increase epsilon to 3 meters, the vehicle does not turn as hard, and it takes longer to settle into the trajectory. See the difference in settling time. Now, if we look into the inputs of the system, we see in the top graph that acceleration is more aggressive when epsilon gets longer. This makes sense, as we see in the picture, because you now have a larger error between your epsilon point and your reference trajectory. However, you would expect the same trend to hold for steering input, or XC. But in the case when epsilon equals 2.5, the input is actually less aggressive, as seen in the bottom graph. This relates to our previous discussion where we explored how the system inputs are scaled by 1 over epsilon. So a large epsilon actually dampens the command input. This trend continues, and as epsilon increases, so does the settling time and max acceleration, whereas the maximum required steering input decreases. Though the length of epsilon acts as a tuning parameter, a key point of this research is that the most significant effect on your system comes from whatever control eye you select for the epsilon point. In our case, we chose LQR, but a myriad of other approaches could have been used for the point. In conclusion, we have shown that non-holonomic constraints for wheeled vehicles can be overcome by controlling a point in front of the vehicle. To avoid the steady-state error, we generate a new trajectory for that point, and we show that it converges. This concludes our presentation, and we're open for questions.